So this is the third day of this 5-day Atal sponsored FDP on flow characteristics and turbulent statistics in the alluvial channel. And this is the third session of today's on the topic measurement and quantification of flow turbulence in the mobile bed channel by Dr. P.L. Patel sir. So it's my privilege to introduce respected Dr. P.L. Patel sir, my mentor also. So Dr. P.L. Patel sir is currently working as a professor in civil engineering department at SVNIT Surat. His area of specialization is water resources engineering. And if I talk about the academic qualification, then sir has received his doctoral degree from IIT Roorkee, and sir started his career as an assistant executive engineer through Indian Engineering Services in 1995, and then he served at Delhi College of Engineering from 1999 to 2007, and then joined SVNIT as a professor in 2007. Sir has received various prestigious awards for the best research papers, best thesis, best PhD work, and best projects, best research projects, like GM Nathawala Award. And sir is invited for the talk on international workshop at Kyoto University in Japan. And sir also worked as a chief coordinator in various research projects of like World Bank project, NCP project related to fluvial hydraulics and flood management. And if I talk about the publication, then sir has more than 120 research papers in the various peer-reviewed journals, conferences, and sir completed more than 10 consultancy projects and guided more than 80 students in UG, PG, and PhD level. And sir as a member of technical societies like in Indian Institute of Engineers, and currently sir is acting as a deputy director at SVNIT Surat. So beside his very busy academic and administrative schedule, sir accepted our invitation to deliver this expert talk in this FDP. So we all are very thankful and lucky to hear sir now. So thank you so much sir for joining here to deliver this talk. So now I am over to you, sir. Sir, you are muted, I think.
Okay. Sorry about that. So thank you very much, Professor Sudhanshu, for introducing me nicely. And I'm thankful to the organizers, Professor Rajesh Jain, Professor Sudhanshu, and other committee members who have invited me for this particular interaction. So I am sure that after some discussion in this particular session, I hope it will be useful to you. So without, I think, wasting time, let us move to the presentation, right? Okay, so I will go in presentation mode. Okay, I hope my screen is visible now.
Yes, sir.
Yes. Oh. So at the outset, just I would like to just I think there's some problem. Or no?
You can cross, sir, on very top side.
Just a minute, I think. Okay, now fine. So okay, so this particular talk which I am going to give is part of the MTech thesis undertaken by my this course coordinator, Mr. Sudhanshu Dikshit. He was a former PG student of mine, and he has done the work, quite good experimental work at that point of time. So what were the results he has received? And those results, in fact, got published in Francis journals, and that is the Journal of Journal of Hydraulic Engineering. It is a Journal of Indian Society for Hydraulics, So that is what I am presenting. So it is a part of the work I am basically presenting. So it is measurement and quantification of flow turbulence in mobile bed channels. It is very nice to see that organizers have chosen very nice topic for this presentation, and that is to getting the funding from AICT Training and Learning Academy, FDP. So I think that will be very useful to our participants. As you know, the topic chosen by them is related with turbulence, and if we talk about the entire, fluid flow processes which we face as civil engineers in our day-to-day life, they are mostly in turbulence in nature. Even if we talk about the flow which is taking place in atmospheric boundary layer, that is also in turbulence in nature, and mostly all the flow which are there in the river, they are turbulence in nature. So if you can say, in fact, we live in the environment which is a very turbulence in nature as far as hydrodynamics is concerned. So basically this presentation would be divided into the following heads. That is introduction, then we have application of turbulence modeling and measurements, then we have previous studies. We will go very briefly on that, and then we will come out what is the objective of our investigation, and then a little bit about theoretical background, and then we will talk about what experimental work we have undertaken at SVNIT Surat, and then the results and discussion we will going to describe on that. But keep in mind here we are talking mostly on the non-uniform sediments, what kind of turbulence which is generated in the mobile bed channel, and that is non-uniform in nature. So basically we have the uniform sediments, we have non-uniform sediments, and considering both kind of sediments, we have tried to see that the turbulence which is generated from the uniform sediment, how is it different than non-uniform sediment. So those kind of comparative analysis also we have tried to include in that presentation, right? So if we talk about turbulence, what is basically the turbulence? So turbulence is basically described the flow regimes which is characterized by chaotic and irregular motion of fluid particles both in space and time, right? So if we talk about, say for example, simultaneously with turbulent flow, we have laminar flow, we have transition flow and turbulent flow. So laminar flow, why this flow is called laminar? Because the flow when taking place in the channel, in the rivers or like that, if the flow is moving in the layers, when the streamlines are almost sliding over one over another, like a lamina. So lamina, I'm sure that everybody may be knowing the lamina. And if the flow, if the streamlines are getting overlapped like lamina, then it is like laminar flow. But in the laminar flow, if you talk about when there is shear stress is always associated with this between the layers. If one layer is moving, then another layer is moving. So between them, there is always association with the shear stress, right? And that shear stress is basically due to the molecular diffusion. Diffusion from one layer to another layer of molecular level diffusion is there, and that is where this shear stress is generated. Momentum is changed, and due to the change in the momentum, we are getting this shear stress in the laminar flow. But if you talk about the turbulent flow, it is not only the diffusion of molecules from one layer to one other layer. It is the fluid particles. Fluid particles move from one layer to another layer, and due to that there is a change in the momentum, and due to the change in the momentum at particle levels when takes place, then you can imagine that the kind of shear stress which is generated is very high. So in between laminar flow and turbulent flow, we have the transitional flow, right? So if you talk about molecules, one molecule, you can see the kind of entity one molecule has, and if you talk about the particle size, if you talk about 10 power 12 molecules can form, a single fluid particles in like that. So fluid particle is consisting of huge number of molecules, you can say. So and that is why when they are diffusion takes place from one layer to another layer, then quite high, shear stress is generated. So the laminar flow having very low shear stress if we talk about as compared to the turbulent flow, right? So this turbulent is of paramount importance for this in our day-to-day life. That is what I wanted to tell you. If you talk about the limit in the open channel flow, Reynolds number is less than 500, then this is a laminar flow. But if you talk about the pipe flow, this limit was in 2000, if you recall correctly, right? But for open channel flow, similarly for turbulent flow, if Reynolds number is more than 2000, then turbulent flow. So this criteria which I am talking about is different than that we talk about the closed flow like that, pipe flow, right? Now, if you talk about the application of turbulence modeling and measurements, it is very, very useful in entrainment of sediments and from the channel bed, because highly, it is dependent on the shear stress entrainment. And if you talk about the incipient motion condition, then precise estimation of sediment transport in mobile boundary channels, efficient design of hydraulic structure. For example, if we are involved in designing the silt exclusion devices like silt excluder, silt ejector, those kind of things, then there's the role of this turbulence comes. Prediction of morphological characteristics of natural rivers. This is another important application. And then design of closed conduit pipes for efficient transport of slurry and sediments, and efficient design of system involving mixing of chemical in the chemical plants, right? So these are a few applications. I just have talked about, but if we talk about the turbulent flow, the application as such it is used, right? Now the previous studies which they have carried out, turbulence study on mobile boundary channels or rigid boundary channels. These are the few studies I have just enlisted over here. Okay, but these are the I'm talking about the very limited kind of references I've shown. But if you the limit turbulence on this study related with the turbulence on mobile channel is many. Okay, so the most important point which we have described is quantification of turbulence characteristics like turbulent intensity, turbulence kinetic energy, turbulent diffusion, Reynolds shear stress, including high order measurements of velocity, fluctuation, and those are basically in scarce in mobile boundary channel, particularly those involving with non-uniform sediments. Studies are maybe available with uniform sediments, but if we talk about the non-uniformity of sediments, such situations, such kind of studies are not very, are not many. Okay, and then also the modeling of transition of turbulence. Again, it is in scarce, particularly non-uniform mobile bed, right? When we talk about the rigid bed and mobile bed, if you talk about, for example, if you take the line channel, if the line channel is there and the flow is taking place in the line channel, it is a rigid bed channel, right? But if the flow is taking place in a river which consisting of the bed and sides, they are having the mobility or the sediments are available on the bed and sides, those kind of the channel beds are classified as mobile channel bed. They can be moved under the action of shear stress. That is what I wanted to say. Uniform sediments, non-uniform sediments. Uniform sediments generally it is being considered as the sediments are practically it is a uniform in nature. But if you have sediments very fine size to very coarse size, and then you can classify those kind of sediments as a non-uniform sediments, right? Similarly, if you talk about this modeling aspect, transition of turbulence means supposing we will describe, of course, that one kind of turbulent bursting event, another kind of turbulent bursting events are there. So how they are, being described for non-uniform sediments, that will also describe over there. So objective of the investigation, what we will describe over here is collection of experimental data for measurement of turbulence in mobile bed channel using a acoustic Doppler velocimeter. Then processing of experimental data for removal of contamination due to noise and spikes before using for further analysis. So whatever the data we would collect generally from this ADV, then that has to be post-processed. You have to post-processing of data after collection. You have to post-process so that you can get the quality data. There should not be contamination in the data. So that kind of analysis has to be carried out. You have to check that whatever velocity data you have collected, whether it is related to fully developed flow or not. That part also you have to take care. In fact, when we collect the data, that has to be collected in the fully developed flow condition only, right? Then quantification of various turbulence characteristics, that is turbulence intensity, turbulent kinetic energy, turbulent diffusion, and Reynolds shear stress along the depth of flow in mobile channel bed, right? Quantification of high order moments like skewness, diffusion factor, flatness factor, and understanding their variation with the sediments of different characteristics. That part also, has to be described, right? Characterization of coherent structure turbulence bursting events over the mobile bed channel for both uniform and non-uniform sediments. So I hope you have studied a few aspects of this coherent structure or turbulence bursting event in these previous lectures. So what is their characteristics for both uniform and non-uniform, that has to be analyzed. And similarly, modeling the transition probability of bursting events using Markov process for both uniform and non-uniform sediments has to be described in this particular work, right? Now, theoretical background, if you talk about, I hope this part might have covered by the previous speakers. But if you talk about here, for example, we must know that at a particular point in the fluid flow, just select the point, and if you start making the measurement, you will get the time. It is time because the time and velocity. So we are measuring the point velocity at a point in a fluid flow, and if you are measuring with time, for example, 3 minutes time, you are measuring. So for example, 0 to 3 minutes. So you can find this kind of variation in the velocity. Velocity is not remaining constant. You can say at that point it is fluctuating about the mean. This cross, if you see the dotted line, that is the mean point velocity, but there is always, fluctuation of velocity, maybe positive side or negative side, from the mean. Okay, so if you talk about U prime, this U prime you talk about, so this is the variation in the positive side. Similarly, if you have this U prime, below a mean velocity, so that will be, in a negative side, if you can say, right? So it's, for example, here, if you talk about similarly, since we are measuring velocity in U direction, maybe in the direction of flow. V prime in the direction of, if you have taken channel in the transverse direction, and W prime, you are measuring the velocity in that vertical direction. So U prime, V prime, W prime are the fluctuation about the mean. Like you have this is particularly for U bar plus U prime plus minus U prime, that will be equal to U. So U is the instantaneous velocity, and you are having the fluctuation maybe plus side or minus side. Similarly, V is equal to V bar plus V V prime. So V prime could be positive or negative. Similarly, W is equal to W bar plus W dash. So W dash means it could be positive or negative. So that kind of fluctuation is there. So that is what I'm saying in turbulence and this laminar flow. In laminar flow, if you make the measurement at the one point, you will get simply this dotted line, mean velocity. You won't get this kind of fluctuation about the mean. But in turbulence, we are getting, right? So that is the basic difference that you have to always understand this, right? Now, if you talk the turbulence field, if you talk about this different velocity distributions, if you talk about in turbulent velocity, turbulent flow, so very close to the bed, maybe order of millimeters, you have very flow, wherein the flow is very viscous in nature, so that is called viscous sub layer. So very fine layer is present very close to it, where the flow is viscous, okay, then that is denoted basically the delta dash. Then we have the buffer layer. Buffer layer means it is the transiting from viscous sub layer to this turbulent wall shear layer, and then subsequently in turbulent outer layer. Okay, so very close to the bed, if you talk about, we have viscous sub layer, then we have buffer layer, and then turbulent wall shear layer, and then in the main flow region, if you talk about in the channel, we have turbulent outer layer. So this is the kind of distribution of the flow. And also if you talk about here that what should be the order of viscous sub layer, then buffer layer, and turbulent wall shear layer. So that is called turbulent inner layer. So turbulent inner layer consisting of these three components: 1, 2, 3, turbulent wall shear layer, buffer layer, and viscous sub layer. And the turbulent outer layer, you are consisting of this free surface layer and intermediate layer, right? So maybe intermediate layer, and then we have this turbulent outer layer. So this is the description given in the Subhas's day book, and that is very good on this morphodynamics book available. Okay. Now, if you talk about this turbulent kinetic energy budget, so maybe depending on if you draw this turbulent kinetic energy and this spectra analysis we draw over here, you find that if you talk about here up to this point, this is basically the energy containing range. Then this intermediate part that is called inertial subrange, and the latter part is called dissipation range. So turbulent energy containing turbulent kinetic energy containing range, where the turbulent kinetic energy comes from the time average velocity. So it is those eddies which are getting generated, they are basically deriving the turbulent kinetic energy from the flow. Then inertial subrange, where both containing and dissipation both are taking place, and then we have this viscous dissipation, when in the whatever the turbulent kinetic energy contained, it is only the dissipation of turbulent kinetic energy is taking place like this. So this is the kind of plot is available. And now we have velocity distribution. If we talk about in this viscous sublayer, so it is mostly basically it is having the parabolic, but since the depth is very small, so generally we take the linear distribution. And similarly, velocity distribution turbulent wall shear layer, that velocity distribution given by this expression and given by the Prandtl logarithmic velocity distribution. So Prandtl velocity, or the pioneering person who has given this kind of derivation for turbulent velocity distribution like that. So here if we talk the U is the point velocity, U star if we talk about the your shear velocity, K is the von Karman Kappa coefficient, and this Z is the depth of that particular point, and Z naught is this roughness height. Okay, so this is there. Velocity distribution buffer layer is neither linear nor logarithmic, because it is there. If you talk about here it is the linear. Viscous sublayer we take the linear, and the upper part this is the logarithmic. So between these two, this layer and this layer, talk about it is the it is not perfectly, neither it is linear nor it is perfectly parabolic. Buffer means it is transition kind of thing. Okay, and then we have this velocity distribution in outer layer, and it is defined by this particular expression like that. Okay, so this is if you talk about this this sigma function 2 pi k kappa sin square pi by 2 z bar. So this is a wake function. This is my Cole's wake parameter, and if you talk about this outer layer, that wake function, it is defined using this particular expression when the wake function is there. Okay, Nico Rotse first observed the effect of bed roughness on velocity distribution. So this velocity distribution which we describe, this the velocity distribution in entire flow, it is basically not independent of the roughness. It is all very much dependent on the bed roughness. Okay, so velocity distribution which we have described, all these, it depends on the roughness of the bed. As you know that classification of flow regimes is very, very important. What is talk about the smooth bed, then we have rough bed, and we have transitionally rough bed, right? Okay. Now smooth bed, when we talk about when the fluid particle, when we talk about these sediment particles, when those sediment particles are totally inside the laminar sublayer, means the eddies which are generated in the turbulent flow, those eddies are not able to touch the roughness, means the sediment particles, and then that your laminar sublayer is acting like cushion. Then in that case, the boundary is called smooth boundary. Similarly, if it is rough boundary, okay, when the complete flow, turbulent flow, your eddies, they are completely touching the roughness, and under those conditions, the hydrodynamically rough boundary condition is there. So smooth bed, you have shear Reynolds number less than 5. Rough bed, if shear Reynolds number more than 70. But if it is between 5 and 70, then it is called transitionally rough boundary, right? So we have to understand, basically, I am talking about all participants present over here. We have to very much clear about the fundamentals of turbulent flow before going for any research in the area of hydraulic engineering. I see many people are going for research, but we talk about a very simple question: what is basically the hydrodynamic boundaries? What is smooth boundary? What is rough boundary? Transition boundary? What is concept behind that? They will just simply say these are limit. But if we talk about that, what is concept? Why this is smooth boundary? What is rough boundary? What is transitionally rough boundary? We have to correlate with this size of the particles present on the bed, or size or roughness present on the bed. Also, the your thickness of laminar sublayer, and the size of the roughness or sediment particles present on the bed decide whether the boundary will be smooth or rough or transitionally rough boundary, right? So, that is what I wanted to explain. Why we have described these velocity distributions. Velocity distribution we have described for almost all the region. Maybe it is the your laminar sublayer region, or could be the buffer region, or could be the wall shear region, or could be the outer layer. Because these velocity distributions are to be checked when we are carrying out the experiment after that, and we have to say with our collected data has to follow these velocity distribution before going for the analysis. Because when our data basically following these velocity distribution means that our flow are fully developed. Again, I am repeating, flow has to be fully developed before carrying out the experiment. So when you produce the results for publication, you have to check during the analysis only that whatever data you have collected, that is there in the fully developed flow condition only. Then the reviewer will accept those results which you are presenting. Otherwise, they will first say that you just check your data whether you have collected the data in your this fully developed flow condition or not. So that is there. I will just explain what is the fully developed flow condition and all those things. So this is the velocity distribution smooth bed. This is for a smooth bed. Okay, is this in there? If you talk about this, U is the point velocity. Point velocity, there is one average velocity. Average velocity, total discharge divided by area. But one time point velocity. Point velocity is the velocity measured at a point on the cross section, right? And U star is the shear velocity. Okay, and Z is the depth of flow where the point is located, and nu is the kinematic viscosity, right? And these are again the for a factor for rough boundary condition, right? And similarly, we have some other parameters also depending on the velocity fluctuation. I have already told that U prime and V prime and W prime, those are velocity fluctuation. So that is there. So we have to represent this velocity fluctuation, and due to the velocity fluctuation, the shear stresses which are getting developed, that is Reynolds shear stresses. Reynolds shear stresses. So this is given by this kind of expression, right? U star is tau naught upon rho. Tau naught upon rho. Tau naught is bed shear stress and rho. Okay. Similarly, you have turbulent intensity. So you can see that your turbulent intensity, if I talk about, that is U prime square under that. So that is called turbulent intensity. And then the expression Ui prime, Uj prime are called second order moments or second order correlation, also the root mean square, right? So RMS of U prime is equal to root of U prime, Ui prime, Uj prime, and you have to take the average of that. But keep in mind that this is the average of product. Average of product. It is not like a single quantity. You take single quantity U prime and simply take the average. That will be 0, right? But if you are talking Ui prime, Ui, then in that case you are making the square of that. Then you are taking the averaging. Ui prime, and after multiplication, so minus minus become plus, and then if you take that mean of that and then square root, then that is called RMS of U prime, right? Similarly, you have the kinetic energy. Kinetic energy is represented by like this, turbulent kinetic energy, right? So these are the few expressions which I will be using time to time. And then these high order moments. High order moments, you can make the presentation in the form of some high order moments, and that's like the skewness factor, right? Skewness factor, and skewness factor can be described in the longitudinal direction and vertical direction, like SU and SW. So this is the vertical direction, and this is the longitudinal direction, right? We have already measured this U prime and this all those parameters, right? Now diffusion factors, similarly, the high order moments is another factor important, and this is called diffusion factor, right? And that is also expressed like this, using these expressions, right? It is a measure of spread or distribution of turbulent fluctuation. Okay, that what is the spread in that this your turbulent fluctuation. Then we have flatness factor. It is a measure of flatness of distribution of turbulent fluctuation, right? So these are flatness factor, diffusion factor, and then we have skewness factor. These are all high order moments. Now, if we talk turbulent bursting events, I will summarize it, but I hope in previous lectures we might have studied that. So if you have collected data, and the data which you have collected, if at a particular instant, if you are having this U prime, W prime, and if you are both U prime, W prime are positive, okay, and then that particular event is denoted as outward interaction. This is outward interaction. And similarly, if W prime is positive and this U prime is negative, then that is called ejection events. Okay, and ejection events are generally called low speed fluid, while outward interaction is generally high speed fluid, right? And similarly, inward interaction, when we have the U prime negative and W prime is also negative, then it is called inward interaction. See, you are here, right? So both are negative. In that case, this is called inward interaction. And similarly, if you have this U prime positive and W prime you have negative, then it's called sweep event. It is sweeping the fluid particle. This is not basically the fluid particles present on the bed. It's all like that. Okay, so quadrant 1, outward interaction. Quadrant 2, it is ejection. Quadrant 3, it is you have this sweep event, right? So this part I already described. If you any particular measurements plot, if you see this is U prime and V prime, W prime, what is positive, this is positive, this is negative, and so on. That I've already told you. Okay. This I've already explained you that what is outward interaction, ejection, sweep, and ejection, like that. Now, organization of bursting events. Organization of bursting events, we talk stable events. For example, the bursting events is, for example, U prime in this current measurements at a time T1, and next you are getting again the same particular feature of the event. So that is basically called stable events, right? That is called stable events, right? So it is stable events means if the current signal is U prime, another signal is also U prime, then it's stable events. But if supposing, for example, marginal events in the previous time you are having the outward interaction, then subsequently you have this ejection events. So you have this outward interaction, then ejection. So that is called marginal events, right? Marginal events. And then similarly, if you have this movement from sweep events to outward interaction, or outward interactions to sweep events, that is called again marginal. So these are kind of marginal events. Okay, so that is there. This is inward interaction, sweep. If the movement is like that, then that is also kind of marginal transition. Similarly, from this quadrant to this quadrant, or from this quadrant to this quadrant, that is marginal events. So marginal events means moving from adjoining quadrants, then we call marginal events. And stable events means remaining in the same quadrants, then that is stable events. And cross events means if you have this is, for example, outward interaction and then inward interaction and movement from and the previously it was the outward interaction, but now it is an inward interaction, so it is a cross event. Similarly, if it is a ejection in the previous situation, previous event, you had this ejection, and but now at this moment if you have this sweep event, so this is again cross. So moving from second to fourth, or first to third, or third to first. So this kind of movement are called cross events. Okay. So this is there. Similarly, you have this modeling of transition probability using Markov process. So there also we have this zero order Markov process, right? Okay. So in zero order Markov process, denote that previous situation does not have any impact on the intermediate situation. Immediate situation. Immediate situation means like another time. Yes, current situation means a current time and the next time. If the situation the next time is not dependent on this current time, or situation in the previous time, and the situation current time. If situation current time does not depend on the previous situation, then that is the Markov process. Similarly, you have this first order Markov process, and we have this Markov process number of I, j, k. Here only we are taking events I and events j. If number of j's follows the i's and total number of i's events are there, then that is called Markov process of order 1, right? Are you getting the point? Number of j's follows i's and total number of i's present over there. So in the previous situation, supposing you have measured data for 3 minutes and you have got that total number of measurement of particular bursting events is following, like for example you have following the outward events. So next time how many events next time is following jf time, it is following the outward events only. So then that is called nij. So nij upon ni, that is called your this Markov of first of order 1. And similarly we have this Markov process of order 2. Okay, so that is there. So okay, first zero order, first order, and then we have the second order. Okay, so these are different Markov processes in the of this bursting events, and different then checking the criteria that whether the collected data from you, whether it is following the AIC criteria or whether following this your order 1, order 2, order 3. So there we use this AIC criteria and BIC criteria. BIC, these are the statistical test kind of thing, wherein we had to check that whatever the data is collected from our experiment, whether it is following this order 0 order, order 1, and order 2. So to check, we have to use these statistical confirmatory tests, that is AIC and BIC, right? So that is available in any statistics book that we can refer out of it. Okay. Now I'm just going to describe more on that. What were the experimental setup which we had prepared in Advanced Hydraulics Laboratory of this SVNIT Surat. So total length L, then width B, and depth H. Length is of 15 meter, width is of 0.9 meter, and depth is of 0.6 meter. This is the kind of length of the flume. And if we talk about, this is the experimental flume we had with us. Okay, still we are having. So this is the basically a pipeline which is feeding water into this flume, right? And if we talk about here, the water is fed from this upstream section over here, and then here we have the sediment feeder. Sediment feeder is available over here, and this is the complete sediment bed. If you can see here, sediment bed is present here in the entire working section from here to here, right? And then we have here sediment trap present over here. Sediment trap is also present over here, wherein we can collect the sediments using this sediment trap. Basically, this sediment trap is designed by us only, and it is now patented kind of sediment trap is there with us. So we got very recently, in fact, this sediment trap patented. Though this particular sediment flume facility was developed when my PhD students were working on that, right? And then we have, this is the tailgate present over here. So with this tailgate, we can maintain the flow in uniform condition, because all the experiments which we have carried out in our lab, that was totally in a uniform flow condition, right? So here the sediments which we have filled in over here, it could be uniform sediments, I have told you, or it could be non-uniform sediments present over there. Okay. Uniform sediment, I've told you, if the geometric standard deviation, you know already, that is the sigma g is equal to root of d84 upon d16. Okay, and if it is less than around 1.4, then we can say that it is uniform sediment. If it is more than 1.4, then generally we classify this non-uniform sediment. This is a thumb classification. There is no universal definition is available, but the concept of uniform sediment is that sediments should be invariably, practically you can say of same size. It should not be much variant from one to another. But non-uniform sediment, you can have sediment size in millimeter, 1 millimeter, or 0.5 millimeter. 2, you can have the sediment of any large size. Maybe you can have 6 mm, 7 mm, or even more than that. There is no limit of that. Means large variation it should be there in the sediment size, right? And after the water is coming in this reservoir, from this again pumped into this pipeline, and again it is feeding into the downstream upstream side. So this is self-recirculating kind of arrangement present over here, right? So I hope you might have understood this kind of experimental setup over there. We had used for measuring the velocity, we have used the acoustic Doppler velocimeter. I think your course teacher, Professor Sudhanshu, might have covered this part, that how to use this ADV, and also maybe I think Professor B.S. Mazumdar was there, so he might have explained more detail about this acoustic Doppler velocimeter. So I won't go much in detail about that, but one point I would like to mention over here is that while making the measurement of velocity data, we have kept this SNR 15 dB. Okay, 15 dB, and minimum correlation should be 0.7. If it is, this correlation is going beyond 0.7 or 70%, then that data is considered as this can say contaminated. Okay, so minimum it should be 70%, right? SNR means signal noise ratio. It is signal noise ratio, right? This is the receivers, and then you have transmitters, receivers. So the transmission of signal is there through this point, and the receivers are there. 3 receivers are there, and from this you are getting the signal back from that particular point. Point is located, this from this point to just a designated volume is there. A sample volume is there at which you just make measurements or like that. So these are a few screenshots of the measurements which we have undertaken previously, right? So now if you take the sediments which we had used in our study, we have taken 0.5 to 1 mm, 1 to 2 mm, and then we have 2 to 4 mm. Up to 64 mm we can use, we have taken, and for mixing the sediments, if you mix the sediments, in desired, sizes. So what we have done is for making the mix kind of thing, if you want to say that we have targeted that this would be our non-uniformity coefficient, non-uniformity coefficient is also expressed using this Kramer's uniformity coefficient. One is geometric standard deviation, other is Kramer's uniformity coefficient. So we have selected the Kramer's uniformity coefficient, and accordingly we have mixed the fluid this sediment particles to get the desired gradation. Desired gradation means if you want to have the gradation of, for example, 2 geometric standard deviation, or maybe your Kramer's uniformity coefficient, if you want to have, say, for example, your 0.02. So accordingly, you can mix the sediments of different sizes and you can get the gradation, right? So these kind of gradations which you have taken, mix M1 and M2. So take this sediment, the geometric mean size is 4.02 mm is for this particular gradation, and this geometric standard DG for this geometric standard size is 3.81 for this M2, right? So this is the data we have collected in our laboratory, and this, if you see that what are the parameters we have taken. So DA is that we have this arithmetic mean size, then we have geometric standard deviation, and then this we have a geometric mean size, and this is geometric standard geometric mean size. We have Kramer's uniformity coefficient. So Kramer's uniformity coefficient, if you can see over here, we have targeted 0.23, right? 0.23 and 0.246. Kramer's uniformity coefficient. From how you obtain the Kramer's uniformity coefficient? First of all, you have to take the sample, carry out the sieve size analysis, and after the sieve size analysis, what you have to do is you have to obtain the value of M from percentage final. So you have 0 to 50. You have to di delta pi upon 50 to 0 to 50. You have to make in the numerator. So multiplication of di delta pi, right, up to 0 to 50, and then di delta pi in denominator 50 to 100. Then you will get the Kramer's uniformity coefficient. These definitions are available in the standard book of sediment transport, mechanics of sediment transport. That is a book written by Professor Rangaraju and Professor Garde. That book is available. Very nice book. You can use for those who are teaching this particular subject, or maybe going for research, right? Definition, I will list these references we talk about, and just refer that. And these are the flow parameters there. So you have Froude number, FR is the Froude number, and this is the Reynolds number. So you must know that how these different quantities are written over there. Okay, so I have told you the post-processing of the moment you have collected the data, then you have to post-process the data for removal of noise, removal of minor disturbance. Okay, on that, and then we have this this removal of noise is, I think, this aspect is taken due to this presence of the noise effect in your this collected data. By keeping this SNR soil noise ratio 15 dB limit, and also this correlation factor 70, right? And then we have to carry out this. We have to remove the the data which are contaminated in the time series, and then we have to carry out this 12-point cubical interpolation. And by completing the time series using this 12-point cubical interpolation, then afterwards, then you have to de-spike the data. De-spike the data means when we are collecting the data and our sample, is not exactly, very above the bed. Sometimes, the influence of particles which are present on the bed, they are affecting our sample. Under that condition, you are getting the de-spiking the data. So de-spike data, the such kind of contamination is also present in this our collected data, and those kind of contaminated data are to be removed using this another algorithm, that is this called phase space threshold technique is there, right? So phase space threshold, you can correct this this error in the spelling. It is a phase space there, right? Phase space threshold method, right? So we have to carry out that particular removal of the spike data using this Goring and Nicora method, and that basically remove the contaminated signals, and again the contaminated signals are removed due to these spikes, and again it is reinterpolated. Again it is reinterpolated, that is a cubical interpolation, and the final data which are received after applying the correction 2 times, one for the noise removal and another is this spike removal, and then that particular corrected final data has to be put in this plot that is called the spectral density versus frequency. And if this for inertial subrange, if it is following -5/3 law, then your collected data is correct, which is following this -5/3 law. If it is not following, means there is some error in the data, and that may be questionable, right? So this all post-processing of data, removal of contamination of removal of data, all those things are very, very important, okay? So now we have to carry out normalized velocity profile. For example, you have collected data, for example, in our working section at 3 particular cross sections, cross section 1 upstream, cross section downstream, and cross section 3 further downstream. And if you collect the data and make the plot, and all the data points are upstream section, then intermediate section and downstream section, all the data are following on particular velocity profile, then you can say flow is fully developed. If it is not there, then your flow is still under development stage, and you cannot say that it is fully developed, and we cannot use your data for your our work. You getting point? So it's very, very important, and we have to see the situation that what the data collected, that is fully developed flow condition only. Fully developed flow condition means your boundary layer is fully developed. Boundary layer is fully developed up to the top, right? Then that is fully developed. If boundary layer is still developing, I mean say just I will explain with the figure. For example, here, if you have started the flow from here, the boundary layer will start developing in the beginning part. So you have to exclude that part, so that you have to have the collection of the data when the flow is fully developed, means boundary layer is fully developed. When the boundary layer is fully developed, and whatever the data collection you will do, then that will be fit to use for your further analysis. Okay, I hope you are getting that point, what I'm explaining that. Okay, so these are important precautions which you have carried out during your these measurements, right? So this is what I explained to you. Now, if you have collected the data and if you can, this is the turbulent velocity profile, and here Ks is the roughness on the bed. So we have also tried to calculate this Ks value. What will be the equivalent Ks value, a roughness value for the bed which we have selected. And if you say that the Ks value which we have 2 dg we have collected, it is perfectly following this logarithmic law for rough turbulent flow condition, and that is what I wanted to explain to you. Okay. Now, while carrying out the analysis, we have carried out the analysis for normalized shear stress like this. So you can see the normalized shear stress by H and normalized Reynolds shear stress. This is the kind of variation of this complete data is there from bottom to top, and you can say that this is almost like linear velocity, linear shear stress distribution. But if we talk about very close to the bed, very close, and that is there in basically the laminar sublayer, and that is where the damping of shear stress is taking place. Damping of shear stress, because the flow is nearly laminar in laminar sublayer, right? So, and otherwise, if you talk about majority of the depth of the flow, where the flow is fully developed, turbulent flow, then you have this linear, distribution of shear stress is there. So Reynolds shear stress increases with increase in the size of both uniforms and non-uniform sediments. So you have seen that how this non-uniform sediments, M11 mix 111, mix 21. So these two are the sediment mixture, and these two are the uniform sediments. So the conclusion which we can draw over here is that near the bed, viscous effects are predominant, resulting into dampening of shear stress over here. Particularly, I'll talk about the second conclusion which you can draw from this figure is Reynolds shear stress increases with increase in size of both uniform and non-uniform sediments, right? And third conclusion which can draw from here is maximum Reynolds shear stress is there at by H is equal to 0.1. Maximum shear stress is here at that 0.1. 0.1, if the maximum shear stress is observed over here near the bed. But if you go beyond, below 0.1, then you can say damping starts, right? Similarly, we have turbulent intensity. So turbulent intensity in, if you say this is the RMSE, root mean square here, okay, RMSE. So if you see that the square root of U prime square mean of that, if you see that, and this is the U star shear velocity. So what you have done, you have measured the U prime, then carried out the square of that, and then you have taken the mean of that, and then you have taken this root of that, and you start. So this is normalized, turbulent intensity, and then you make the plot. So you can see from this plot also, turbulent intensity in longitudinal direction decreases with increase in the size of sediments. Okay, you see the maximum one is this. So you can see here, this is the 5.65. That's the coarsest one. So this is the maximum. Okay. So similarly, in turbulent intensity in vertical direction, W prime square. So turbulent intensity in vertical direction increases with increase in size of sediments, right? This is the turbulent kinetic energy. Turbulent kinetic energy. So if you can see here, turbulent kinetic energy. So the plot of turbulent kinetic energy by H. Okay, and if you make the plot of that, turbulent kinetic energy, I had explained the previous equations. If you talk about that, just a minute. Is this the turbulent kinetic energy, right? So this figure you can take. Okay. U prime square is mean, then BB, all the three direction velocity you taken, and then you have calculated the energy there. So we're talking about this turbulent kinetic energy, okay, and then you can see the kind of variation is there. So turbulent kinetic energy increases with depth near the bed region. So you can see here it is increased very close to the bed, right? And then in maximum at 0.1, 0.1 it is maximum, and then decreases in the outer layer for both uniform and non-uniform sediment. We have plotted both data for both uniform and non-uniform sediments, so there is decrease, you can say, beyond that. And turbulent kinetic energy are consistently higher for coarser sediments. Turbulent kinetic energy is more for uniform sediment vis-a-vis non-uniform sediments. We say this is uniform sediment and non-uniform sediments, right? You can say uniform sediment, this symbol, this. So this is the uniform sediments, and this is again this uniform sediment. So if you say correspondingly, what is happening to this our non-uniform sediment? So this is there. So similarly, turbulent diffusion. So turbulent diffusion basically increases. Coarse side is the negative side. So turbulent diffusion, because this is minus 12,000, 9,000, 6,000, like that, it is there. So turbulent diffusion increases with coarseness of sediments, and turbulent diffusion is higher for non-uniform sediments, right? Non-uniform. So again, the non-uniformity is more in case of non-uniform sediment. This turbulent diffusion is more in case of non-uniform sediments vis-a-vis uniform sediments. And turbulent diffusion in vertical direction, if you talk about this particular plot, and wherein we can have this is the turbulent diffusion in a vertical direction. So this is your plot for this is for your coarser non-uniform sediment, and this is the finer one, this one, right? Triangle, upper triangle, right? So turbulent diffusion in vertical direction is maximum in outer layer at larger depth, right? Larger depth it is higher, and turbulent diffusion in vertical direction maximum for coarser sediments. Two conclusions which we have drawn from here, from this particular plot. Okay. Similarly, you can have high order moments. So you can see the kind of variation. High order moments, that is skewness factor. So what kind of variation therefore skewness factor? If you talk about this SU in longitudinal direction, and this is in a vertical direction, right? Okay. Skewness factor. So if you can say that the SU skewness factor near the bed are close to zero, right? Very close to zero. The SU near the bed are close to zero up to y by h less than 0.2, right? Okay, and is skewed towards the left at higher depth, y by h approximately greater than 0.2. Okay, so see, this is 0.2. Okay, beyond this going like this, and then beyond this going like this. So it is 0, it is like this. So you can see the kind of variation we have over here. Okay, so if you draw a vertical line from here, 0.2, and then see the kind of variation which we have. And this is the skewness factor in the vertical direction. If you see here, okay, near the bed are close to 0 again. It's close to 0. This is 0. Okay, this is close to 0, and then skewed marginally toward the right at higher depth. Okay. The value of SUSW lies between 0 to minus 0.3 and 0 to 0.3, right? So this is there. Similarly, we have a diffusion, this factor, variation of diffusion factor. So diffusion factor near the bed are positive, while it is negative at higher depth. Okay, it is 0. So positive, very close to the bed, very close to the bed. It is positive because this is 0. So if you draw a vertical line, you can see very clearly here it is positive, here it is negative. And similarly, kind of situation, if you can see here, very close to bed it is negative. If you draw a vertical line, so here it is negative, and then forward it is positive. Flatness factor. Okay, so flatness factor, you can see here, flatness factor is related to intermittency of turbulent bursting events. FW lies between 2.7 and 10.5. Entire values are lying between 2.7 to 3.5. This complete range is there defined, right? These are transition probabilities. That complete analysis is there. Basically, I always show the paper. One paper, if there on complete this analysis, you can refer that particular paper, and then I think you will get the complete results. So these are two papers which we have published on that, and this is one paper which we have described the results over here. This complete paper published in Characterization of Flow Turbulence Mobile Boundary Channel. So this is there. So you have the complete details of the paper. So what was the description which we have done here? This is a call available in this particular paper. So you can refer that particular paper for complete details which we have described in 1 hour time. Less so, please go through the paper, and that will definitely give you the complete details of description of what I have explained over in this paper, right? So this is there. So if you can see that in our analysis, we have found that first order Markov process is basically following this complete occurrence of probabilities of events, right? So from this analysis, you can say this AIC and BIC, wherein it is minimal value. So for example, this is 0 order, this is first order, this is second order. So you can say these AIC and BIC values are minimal for this first order Markov process. So it can be concluded that first order Markov process is most appropriate in modeling the transition probability of bursting events, right? So that is there. Okay, and then I have drawn few plots are also available on the paper, and you can see that when we have plot number of bursting events, outward interaction, in ejection, inward, and sweep. And if you can see here, you can say that at y(h) equal to 0.1 here, if you say this particular point, wherein you can say that it is seen that the sweep and ejection events are predominant for the entire flow depth, sweep and ejection. This sweep is this cross one, and ejection is this red one. So this is the dominated. These two events are dominated, entire depth. But on other hand, inward and sweep, they are having the minimal values or lower values over there. So at 0.1, it is a maximum. This is minimal values. Similarly, for this, you can say for uniform sediments, U11, U21, and similarly, you can have this is the kind of variation for you have non-uniform sediments and like that. Okay. Then we have this stable events. Then we have your cross events, and we have seen that is marginal events. I've told you what is the stable events, what is the marginal event, what is the your outward events, this cross events. So it is apparent that percentage stable events are marginally higher for non-uniform sediments bed than uniform sediment. The situation is reversed for the marginal cross events. So those kind of analysis we have tried to carry out and get the preliminary kind of signature for the uniform vis-a-vis non-uniform sediments, right? So this is there. Now I would like to draw the conclusions from this. That first of all, this is not very good. I mean, very common kind of finding, but you can say always that we have carried out our study in fully developed region. This is not conclusion basically, but yes, we have ensured that before using the data, our data were fully developed. Now the second point, Reynolds stress distribution followed linear distribution in the outer flow layers with maximum value being closer to the bed. Okay, and beyond that we have this effect of laminar sublayer, and then damping effect comes. And then we have turbulent intensity in longitudinal direction, and turbulent kinetic energy increases with increase in the size of sediment, both uniform and non-uniform sediments. Okay, so this another conclusion. The turbulent intensity and turbulent kinetic energy were found to be maximum at point y(h). Y is the depth, h is the total depth. So it is 0.1. Then turbulent diffusion in the vertical direction is maximum in the outer layer at larger depth. The turbulent diffusion in vertical direction is maximum of coarser sediments. And similarly, we have the skewness factor and then diffusion factor in the vertical direction increases from negative at the bed to the positive value in the outer layer, while SU, DU decreases with increase in the pi IH beginning from positive value near the bed. And similarly, the value of Fu and Fw lies between flatness factor in the longitudinal direction and vertical direction lies between 2.7 to 3.5. And that basically in line with this previous investigator like Billigan and this Krogestan and Ramesh and Kothari. First order Markov process is most stable in the modeling, most suitable. In fact, the first order Markov process is most suitable in the modeling, and the transition probability irrespective of the type of sediments, right? Maybe uniform or non-uniform. Sweep and ejection events were found to be dominating over the outward and inward interaction events for both uniform and non-uniform sediments. Stable events are marginally higher for non-uniform sediments bed than the uniform sediment bed. The situation is reversed for the marginal and cross events, right? So these are the few references. This is the book, a very good of fluvial hydrodynamics. The book is written by Professor Day from IIT Kharagpur, and this is a very nice book. You have to refer these two papers, which I have. My lecture is based on. Complete details are available on published in 2015 and around 18. So you can refer that particular those particular discussion in detail, basically to understand the situation. And then we have this all other references there with us, right? One book, of course, I forgot to write, but you can see that book of mechanics of sediment transport, and that is the fluvial hydraulics. That is Professor Gardi and Rangaraju. That book you can refer. That is a very good book. Okay, so these two books and these few papers you can use those who want to carry out the research over there, right? So thank you very much. Thanks for inviting me to be part of this particular event and interacting with us. If you have any question, please come forward.
So if there are any questions, then you can ask. Is there any question?
My request to the participants is there. Maybe this particular lecture, maybe involving both sediments and uniform and non-uniform sediment, then understanding this complete, this bursting events. Maybe they be feeling this a little difficult, but please, this subject, if you're going for this experimental investigation and if you are showing some publication to the journals, this is generally getting accepted because you are carrying out something and you are putting your results in the form of publication. So they generally, accept that. Carry out the research in terms of, on computer-based software like that. So that is there, but if you go through the books and if you go through the papers, I think you will get it out. Okay.
So we are very thankful to you, sir, that beside your busy schedule, you have accepted our invitation for delivering this lecture. Hope all the participants have learned a lot from this lecture and it will help them in their future research work. So at present there are no questions, I think. So if we've got any question, then we may mail to you, sir.
No problem. If you have any question, maybe related with the turbulence events, or maybe you're related to sediment transport, yes, you are most welcome. And you can write to me. You can write to Professor Jain. Professor Rajesh Kumar Jain. He's there already, and he will be definitely solving your problems. But you can give the question to me also, and maybe Professor Sudhanshu also. So that is not a problem. But your questions are most welcome.
Yes, thank you very much, sir, for sparing your time.
Thank you, sir. Thank you, and for inviting.
Since 2-3 days from all the way from Bilaspur, and you kindly agreed upon this schedule for this schedule. and we are obliged for that, which we have spared as 1.5 hours to from your busy schedule. Although the participants would be listening, but probably since from morning they would be tired, so they are not able to ask questions or they would be in mood to leave out.
No problem. No
Session
problem,
was
sir.
very good.
In fact, it is pleasure for me to be available for this kind of program.
Yeah,
But I'm sure that these participants will be in touch at least with this background, and they will take their career in that direction. Right, sir?
sure, sir.
Sure. Thank you very much for
Thank you,
inviting
sir.
me. Thank you. So nice. Thank you.
Thank you, sir.
So I hope all the participants now have in-depth information about turbulence, its application, different types, basic definitions, measurement of turbulence, how we can measure, what are the procedures for experimentations, what are the key points that we have seen in the today's lecture. So in the last session we have summarized all the things that we have discussed till date regarding core turbulence. What is turbulence? What is the laminar? What is how boundary layer formation is there? Flume experimental work, stochastic analysis, stability analysis. So if you are carrying out this type of work, then definitely it will get published in a very good research journal paper. Okay. And if you find any difficulty, then you can contact to us.
Okay, sir.
Okay. So, sir, we can conclude the session now for today. Hello.
Yes, I think as such there is no query raised from the participants. So I hope we can close it and sharp 11
Yes,
tomorrow
yes.
we can start.
We have shared both the papers also that were mentioned in the reference section. So you can refer that papers, and along with that I have shared some other papers also. So
Distance,
that will help you.
Sudhanshu, just wait for a minute. The Dr. Ajay has seen one presentation and video. So actually, Roshan has raised one query in morning. So just I would like to share
Okay,
those things.
yes, sir. Yes,
Right.
sir.
Just wait a while. Uh, so it is just getting downloaded. Wait for a minute and we will start. Yes, some photographs are here. Just I'll share this presentation. Slideshow from. Wait a minute. My screen is visible?
Yes, sir.
Yes,
Yes, sir.
visible, sir.
Okay.
Yes, sir.
Sir.
Wait a minute. On current slide, I'll just go here. See, these are few photographs which he has sent to me. Let me first just surf these photographs, then we'll discuss. This is in gravel mixture. The spur dike is placed. Then it is in sand gravel mixture, another photograph. Now, he has also conducted some pier scour experiment. So, this pier was inserted in gravel mixture, I think. Then this is another view, a very good view of scour hole developed. You can see this is the scour hole, total scour hole from here to here, and deposition on the wake of the scour hole, which is not visible in this photograph. Now, this is what partially submerged dike, the photograph of this one. If I can get another, yes. So you can see this flow of water from here. The depth, full depth is not submerged. Dike is there. Some portion is submerged in bottom, which is not visible due to dirty water, and this is what the portion which is visible. So this is partially submerged dike. Then this is the fully submerged dike. You can see the dike is here, and the water is passing over the top of the dike, and there is development of scar hole. Roshan, are you looking it?
Yes, sir. Yes, sir.
Right? So
I'm
this
looking
is
it.
submerged dike,
Yes.
which is not visible. Even partial, a single line is visible, and you can see this turbulence is developed here in this portion where the sediment eroded due to the flow of water, and that you can see. So submerged dike, and this is the one video he has sent from there, live experiment when he conducted during his research work. So you can see now these are the structures, vortex flow, you can say, or turbulence. What these things we are measuring through the ADB. The idea of or theme of the whole course up till now, whatever we have discussed. Let me play again. This would be very good. Wait a minute. Yes. So this whatever you can see, there's all reverse flow or eddies, little eddies you can witness. So these things will not be able to be recorded by any instrument other than ADV or Neutrino Plus or any instrument which is in measuring three-dimensional flow pattern. So while running this spur dike, ADV was inserted in this plane, which he has shown in the morning, and at various locations, he has taken this ADV measurement. So submerged dike, then this you can see velocity measurement near submerged dike. So this is ADV. It is immersed here, and this dike is there. This white line is dike. So actually, he should have shown this photograph in the morning, but he could not add these photographs in his presentation. So this is ADV, Sontag ADV. Only you can see this thumb or the upper hand. The lower hand is submerged in water, where it has three probes, and it is connected to a cord and recording this all observations. So that is for submerged dike. And these few pictures he has supported in his presentation, which in morning he could not shown to you. Rushan, is that all right?
Yes, yes, sir. Yes, sir. Thank you, sir.
Probably you can get the difference between at least submerged dike. This is one submerged dike, and
Yes,
partially
sir.
submerged dike. So
Partially submerged.
yeah, that
Yes,
that.
sir.
But deposition probably is available in this picture only. See, this is sand gravel mixture, and you can see this dome or rather hump or bund. You can say one bund is made here of these particles which are removed from here. They are getting deposited here.
Yes.
Similarly, in this pier scour and all this. So with this, if any doubt in up till now, whatever we have completed more than 50%, 60% of the short-term training program is completed. Around 9 lectures we have covered. If any participant has any doubt up till now, he is most welcome to share his doubt. We would be able to clarify from our side or through the experts also. Over to Sudhanshu. Your mic is not on, Sudhanshu. Sudhanshu, your mic is not on.
Yes.
Yes.
So today we have completed the third day of this FDP. Tomorrow we are having the fourth day of this FDP, and very first session is on vector analysis of flow pattern during scouring around the pier by Dr. Ashish Kumar. Then we have a lecture on near bed particle motion sediment laden flow by Dr. B. Ramesh, principal. And last lecture is also near bed turbulence characteristics in sediment laden flow by Dr. B. Ramesh, principal, Savinita School of Engineering, Chennai. So I think tomorrow you will have some exposure to the, I think, some more advanced techniques for measurement of the turbulence by capturing some images like I think PIV or high speed cameras they have used for in their research work. So now we are closing
I
this
would
session.
also like to add one thing that tomorrow all three sessions would be very interesting as far as the recorded data are shown to you. In first session, Dr. Ashish will depict you how you can plot the vector of whatever velocities are measured, and vector analysis he will do. So that will also be helpful to you. And as well, this high resolution camera, as I have been talking in my lecture, that recording जैसे अभी आपने देखा स्पर डाइक में पानी बह रहा है and you want to record below the water, that is not possible with your ordinary camera. You cannot see inside the water. So in Roorkee, during his study, he had got this high resolution camera, and he recorded those observations he would like to show to us. So tomorrow, don't miss this first and second session. It would be very much useful to you. Yes, that's all.
Okay.
Okay, sir.
Okay. So thank you all the participants. We will meet again tomorrow at 11 a.m.
Thank you so much, sir.
Okay.
Thank you,
Thank
sir.
you, sir.
Thank you.
Yes. Thank you.
Thank you.
Thank you, sir.
Thank you.